Hi and welcome back everybody. So we're headed into the graphing component of the course where we're going to begin to graph sine and cosine functions and various other trig functions. This podcast will devote to sine and cosine. I wanted to mention that it's tempting to use our graphing calculators, but I'm going to start us off just thinking everything by hand and doing it the old-fashioned way. So many things in daily life repeat with a predictable pattern, such as weather, tides, and hours of daylight. This periodic graph represents a normal heartbeat. It makes sense that many natural phenomena are periodic and can be modeled with sinusoidal graphs. Thus, we spend a significant amount of time in this chapter getting familiar with period, amplitude, phase shift of the various trig functions. Okay, let's scoot down to sine and cosine. Now, I wanted to mention with this table, no need to memorize it. We will naturally discover these things as time moves along. So just for starters, as S increases, so as when you're living on the unit circle, S and theta are synonymous, right? So as your angle increases from 0 to pi halves, the values of your sine function will increase from 0 to 1. But the values of your cosine function will decrease from 1 to 0. And I'll let you peruse this table, but like I said, you're going to notice these things. Just take note as we begin to graph. So take notice of these things as we progress. And you might even revisit that table later on. Okay? Let me scoot that on down. Let's just jump into an example together. Graph f of x equals sine x, where x is in radians, and let's explore this using technology a bit before we talk about how to do it by hand. So, and you see I have my calculator screen right here. So you could just type in your y equals, go to y equals, hit, type in sine of x, make sure you're in radians, and then if you're on a TI-83 or 84, remember that you want to hit zoom trig to get your classic window from negative 2 pi to 2 pi. Okay, now the thing that I really wanted to take notice, and I'm going to zoom in even more, take notice that, origin is right here, and then we're rising as we approach pi halves, and then we're falling as we approach pi. We're still decreasing all the way to 3 pi halves, and then we start increasing again. So the question is, how would one, if I didn't just type this into the calculator, how would I produce it? And herein lies the answer. You do a table of values. So you're noticing that the domain, this is just from the calculator, that the domain is infinite, negative infinity to infinity. You're noticing the range is negative 1 to 1. So, your lowest y value is negative 1, your highest y value is capped off at 1. Okay? Now you say, all right, and you can see visually that the period, how long it takes to repeat itself, the period, I'll sketch it in black, is here, from 0 to 2 pi. So the period's 2 pi. So notice if we're going to make a table, we're going to start at 0 and we're going to end that table at 2 pi. So soon we're going to talk about a recipe for sketching by hand. So if we sketch over one period, then we'd be sketching from 0 to 2 pi. If we sketch over 2 periods, then we do negative 2 pi to 2 pi. But before we, talk about anything by hand, just take note of the following. Okay? The graph is continuous over its entire domain. That means you don't see any holes or jumps or gaps or breaks or vertical asymptotes. The x-intercepts are of the form n pi. That means they happen at integer multiples of pi. So you can see the intercepts are at 1 pi, 2 pi, 3 pi, 4 pi, etc. The period is 2 pi. The graph is symmetric to origin, and you remember from college algebra, if you have that origin symmetry, you're considered an odd function, right? So that sine of negative x is the same as negative sine x. So that comes from college algebra being an odd function. Okay? Now let's take a look at cos x. And again, I'm using the technology to graph it for starters, but I could just produce a table of values. Now, relying on the unit circle, which we'll talk about in a moment. So let's just say you typed in, y equals cos x, and you were able to produce this graph on your calculator, you might notice that cos x, doesn't start, it starts up at that key point there, 0, 1, right? And then travels along, and it looks like, I'm doing a bad job of highlighting it there, but it looks like its period is also 2 pi. You see its domain is infinite as well. You see its range is -1 to 1, just like sine. So just start to notice things. And then if you think about it, think about putting 0, just good old-fashioned table values. Put 0 in for x. Well, cosine of 0 is 1. See? So you could do plotting points. And then think about pi over 6. Think about these key values along the unit circle, right? So pi over 6, pi over 4, pi over 3. And you could think about what cosine is at those respective values. Okay? So cosine of pi over 6 is √3 over 2. Now I'm going under the general assumption that you're comfortable with the unit circle. We're going to play with that in a moment. Cosine of 2 pi is 1. So if you were to plot those points, which we're going to do in a moment, you would quickly see that wave. All right? Now again, just take note of the properties of cosine x before we go doing anything by hand. Notice it's continuous over its entire domain. The x-intercepts are of the form 2n plus 1 times pi over 2. So that, when you say like that, where n is an integer, that's odd integer multiples. So that's a way of saying odd integer multiples of pi over 2. So if you think about that, it's 1 pi over 2, 3 pi over 2, 5 pi over 2, etc. for the x-intercepts. The period is still 2 pi. The graph is symmetric with respect to the y-axis, so it's considered an even function. And again, that's back to if f of negative x sends you back to f of x. Remember that was sort of our test in college algebra for being an even function. Or we also would say it has that symmetry with regard to the y-axis. Okay, now we're ready. All of that, and I was ready to do an example with you. Okay, so graph y equals 2 sine x and compare it to the graph of sine x. So we have a general recipe, and I wanted to talk about that. You want to take the period of sine x, divide it into 4 equal intervals along the x-axis to get started, as seen in this table. So I'm actually going to zoom back out here a second. So I'm going to zoom this way over here so I have plenty of room to write. So if you have y equals 2 sine x, just think about this. The period is 2 pi. You're going to chop that period into 4 equal parts. Okay, so 2 pi divided by 4 is really 2 pi over 4, which is really pi halves. So what that means, think about it like this. Here's 0, here's 2 pi. That means your first notch is at pi halves. First notch. Your next notch is pi halves plus pi halves. So half pi plus a half pi is a full pi. Right? And it's like every notch you add on another pi halves, so you definitely deal with fractions. Next one's going to be 3 pi halves. Okay? When you divide up the interval from 0 to 2 pi, aha! Notice all of these little notches are what's in the table here. You see? So I'm going to zoom back out. See, that's how you know. A lot of people are like, how do you know what to pick for your x values? That's how you know. So you're chopping the x-axis at those partitions. So partition the x-axis into 4 equal intervals. All right, we did. And then just evaluate it. So just store 0 in for x. Well, sine of 0 is 0, and 0 times anything is still 0. Now, just to further illustrate, store pi over 2. Y equals 2, and so you don't have to do the mental math. Let's write it out together. Well, what is sine of pi over 2? Sine of pi halves is the y value on the unit circle, right, at that location, which is 1, and 1 times 2 is 2. So that's why So, this part will go to 1, but then you're multiplying that by 2, so you're arriving at a 2. See, 2. And then likewise, just keep doing that. Plug in pi. Well, sine of pi is 0. 0 times anything is 0. Now, the cool part is once you fill out this table, okay, etc., once you fill out this table, it's just plotting points from there. And I wanted to actually, I'm going to zoom back out so you can see that. Okay. If I am freehand sketching this, what you do is nothing fancy. You just sketch in 0, pi halves, put little, put notches where you said you were going to put them, pi, 3 pi halves, and 2 pi, okay? And then just literally plot the points that you found. So 0, 0 is a key point. I'm just reading from the table. At pi halves, you're up at 2. At pi, you're at 0. At 3 pi halves, see, I'm retrieving, note to self, I'm retrieving from this table. At 3 pi halves, you're down at -2. Boom, boom. So at 3 pi halves, you're down here at -2. And at 2 pi, you're back at 0. See? And connect the dots, and voila. You have yourself a period of that function, y equals 2 sine x. Let me zoom back. And you can see visually, then you can start to make the connections, and you could even plot them both. Say you plotted them both on the same grid, or even on your calculator. You would see that y equals 2 sine x has higher waves, right? And that's a way of saying a larger amplitude. So we see the amplitude on that is 2 versus the amplitude on this one here is 1. Okay? So we have begun to notice something about the amplitude as it relates to y equals a sine x. The amplitude is a. I'm going to hit pause as we go to the next slide. Okay, so thanks to the last example, we started to notice about amplitude. The amplitude of the periodic function is half the difference between the min and max values. I like to think of it as the height of the wave from the x-axis to the top of the wave. It describes the height of the graph both above and below the horizontal line passing through the middle of the graph. That's if you're a visual person. If you have y equals a sine x, the absolute value of a is your amplitude. If you have y equals a cos x, the absolute value of a is the amplitude, and you see that here. So you just want to bear that in mind as we proceed. So no matter what the value of the amplitude is, the period of a sine x and a cos x are still 2 pi. That's good to note. Let's begin to look at some functions where the period though has been affected and is no longer 2 pi. Well, we need some general theory before we do that. So if you have y equals sine beta x or sine bx, the period is 2 pi over b. If you have cos bx, the period is 2 pi over b. So note to self, be on the lookout for the coefficient of x. Okay, and that'll trigger you for your period 2 pi over beta, where beta is the coefficient of x. Okay, general guidelines for sketching sine and cosine, and we mentioned this earlier, but here it is in words. Find the period 2 pi over beta, and lay off a distance of from 0 to 2 pi over beta, like on the x-axis, and divide that interval into 4 equal parts. And evaluate the function for those respective x values that you had found in the part above. And plot the points and connect with your wave-like function. Okay? Let's scoot that down. Plot the points found and join them with a sinusoidal curve having amplitude a, absolute value a, and then draw additional periods if needed. Sometimes they tell you to draw it over 2 periods or 3 periods, something like that. Here we go. This is what I've been waiting for. One like this. All right, let's put our thoughts together in this lovely example. So you have y equals -2 sine 3x, and they want us to sketch it over 1 period. Well, right away we know absolute value of -2, which is 2, is the amplitude. So we can be on the lookout for that. Okay? We also know that 2 pi over beta, where beta is 3 here, so 2 pi over 3 is the period. Okay, now the catchy part. I'm going to zoom this back over and try to follow the recipe so you can see, how you get the table. So you take the normal period of sine, which is 0 to 2 pi, and you think about the fact that it's been affected now, and you have to chop that into 4 equal parts. So the period of this, I like to think of it as this transformed function. The period of this is 2 pi over 3. So we have to take 2 pi over 3, so take period, divide it by 4. All right, well, if you do that, you're going to have 2 pi over 12, which is pi over 6. So that means, here we are, 0, first notch is pi over 6. Next notch is pi over 6 plus pi over 6, which is 2 pi over 6. And a lot of people say, yeah, but 2 pi over 6 is a 1/3 pi. I know, but don't. I like to keep it not reduced because I think it looks prettier temporarily. And then 2 pi over 6 plus another pi over 6 would lead you to 3 pi over 6. And then your last endpoint would be 4 pi over 6. And notice that 4 pi over 6 reduced is 2 pi thirds. So you should end, note to self, you should end at exactly where the period is on this, which is 2 pi over 3. So you know you've chopped it up okay. And big note to self, you have to practice chopping that x-axis into 4 equal parts like that, and notice that those partition values are the exact values that occurs in this xy table. You see that? So that's how you're going to know how to make your xy table. So you partition the period of this function, y equals -2 sine 3x, partition it into 4 equal parts, means divide by 4. And when you get pi over 6, that tells you where your first notch, I like to think of it as your first partition value, is at pi over 6. And, and then you keep adding pi over 6. Until you get to your endpoint. So you're looking over the interval from 0 to 4 pi over 6. Okay, well then the fun begins. Let me zoom back out. So you might be thinking, okay, take 0, store it in. Well, sine of 0 is 0, so we know that output value is going to be 0. Now let's take pi over 6 and store it in. Now if you don't like mental math, you're going to want to write this out. So -2 sine of 3 times pi over 6. But if you think about that, that's -2 sine of 3 pi over 6, which is basically pi halves. But again, sine of pi halves is 1, and 1 times -2 is -2. So I'm looking... Oh, I'm seeing here that it actually just got cut off. The bottom part got cut off. This should be -2. This part cut off is still 0. Okay, the very bottom part of the table got cut off there, but I'll fill it in with you. Let's try again. Take pi over 3 and store it in there. Let me erase this. And again, you see that I don't have to do the mental gymnastics. I can physically store it in. Take pi over 3, store it in, write it out. Okay, y equals -2 sine of 3 times pi over 3. Well, the 3's are going to cancel, so then you're looking at sine of pi. But sine of pi is 0. So you end up with -2 times 0, which is 0. See? So the output value on that should have been 0. Okay? So this little part here that got cut off was the full-blown function, -2 sine 3x. Okay? So this is 0, this is -2, etc. And you could see where the rest of that table came from. Now notice when you plot the points, you're just taking those key points. Remember we talked about partitioning the x-axis, and I'll just redraw it. Partition it where we said to partition it. So pi over 6, pi over 3, pi over 2, 2 pi over 3. Remember, your end point should be what you claimed was the period. And then you literally plot these points. So 0, 0. At pi over 6, you would be down at -2. At pi over 3, you'd be, so I'm reading the bottom line here, you'd be at 0. At pi over 2, you'd be up at 2. Pi over 2, you'd be up at 2. And at 2 pi over 3, you're back down to 0. You see? So you've sketched a period, and I have it here. So you've sketched a period of that function. Now, I did want to note to self, when a is negative, notice here, the graph of a sine bx is a reflection across the x-axis. So you are noticing that, you know, the fact that there's a negative out front has sort of flipped your sine function across the x-axis, just like it did in college algebra when you were graphing like negative square root of x, right? And you talked about reflections. Same thing is occurring. Okay, now let's scoot on down here to -3 cos pi x. And now I just want you to practice, okay, 2 pi over beta. But notice that beta is pi, so 2 pi over pi, so 2 is your period. Well, notice that you're taking the period and cutting that into 4 equal parts. So 2 divided by 4 is 2/4, which is a half. So notice your first, and I'll zoom in, notice your first partition value, then, you know, 0, a half plus a half is a whole, and then 1 1/2, which is 3 halves, and then eventually at 2. So you can see that that's here, 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 right? The partitions. Now you know the trick. Since those are your partition values, you can just go for it. Store 0 in there. Well, pi times 0, 0. Cosine of 0 is 1, but 1 times -3 is -3. Now you see why the point 0, -3 exists on there, etc. And, you know, go ahead and take a half. Store a half in there. Well, pi times a half is pi halves, and cosine of pi halves is 0, and 0 times anything is 0, so now you see why that point is there, etc. So I'll lead you to decide why these key points are on that curve, but in practice, I think the tough part for most people is just partitioning the period into 4 equal parts. Once you have that, creating your little XY table is going to be easy. You'll just use 0, a half, 1, 1 1/2, which is 3 halves, and 2, right? And you know at 0, you're going to get out -3. At a half, it'll be 0. At 1, it'll be 3. At 3 halves, it'll be 0. And 2 will be back down to -3. So you can verify that. Okay? And let's see the next one that we have. Oh, this one I thought was sort of cute. You can almost, this is like working backwards. Determine an equation of the form y equals a cos bx or a sine bx, where b is greater than 0 for the given graph. Well, think about it. It takes 4 pi to repeat itself, right? So that means the period is 4 pi. Well, that means that 4 pi would have to equal 2 pi over beta. And you're solving for beta, which is the coefficient of x, right? So if you just kind of cross multiply and solve, you'll quickly figure out that beta would have to be 2 pi over 4 pi. Pi's cancel, so beta's a half, right? So now you can see, and I have the answer pasted there, the answer ends up being y equals -2 cos 1/2 x. So now you see why the coefficient of x is a half. It's because you'd have to solve for beta, okay? The other thing is, you might be wondering, how come -2? Well, you see the height of the wave is 2, but the thing is, if you didn't make it negative, it's a reflection, right? So if you would have tried to say 2 cos a half x, I always say do it wrong on purpose and see what happens. If you would have said 2 cos a half x, you would have seen it starting up here. Okay, it would have went like this instead. It would have went the opposite direction. So what I'm getting at is the lead coefficient on that is going to have to be negative. Note to self, because you have cosine reflected. Okay? All right, hope that helps. Now we do have one other slide, but I think I'm going to save that for a separate podcast. I think it's on using graphing calculators. Yeah, so slide 3 here is on graphing calculator usage. So look out for this on the next podcast. Okay, we'll try to play with our calculators. All right, good luck out there.